Yeah. So good morning, everyone. Today we have John and his team members for presenting on the MaxE project update. As we know, John is our SA astronomer and a team member of the MaxE project. Let's welcome John and all the team members to the colloquium. And I kindly request John to introduce other team members to us. And over to you, John.
And we'd like to keep questions till the end so that this just flows more seamlessly. Okay. Right. Well, the last time we talked to the community about MaxE was in January last year. So we felt that it was about time that we presented some indication of what progress had been made and what the future holds for MaxE. In this talk, we're talking, I will talk about a little bit, remind you about the science case and the system design that we've come up with. Yannis will talk about expected performance, Orchid about the instrument layout, Catherine about the detector, and Routurd about the project. Just to keep everybody straight, MaxE is the name of the project. So it connotes nothing more than simply it's a name that we use to talk about everything. RSS Jule is what we are aiming to produce. This is the name of the spectrograph, and it will comprise the existing RSS, which we've renamed RSS Viz, and a new arm on the, which I'll get to eventually, which we'll call RSS Red. This is the team. It's managed by Routurd from Sorel. I'm PI at the moment until sometime early next year when we expect Lee Townsend to take over. Optics is under the control of Yannis Brink and Melanie Simon. Opto-mechanics, Orchid Stratum and Farid Ibrahim, who used to be at SALT, that's now at Sorel. The detector team is large and diverse, led by Catherine Rosie, with Peter Swanefelder, electronics, James O'Connor, mechanical, Tapua Makambori, mechanical or engineering in general, and all under the BDI of Hitesh Gajar. Stephen Hume's responsible for control software and electronics. And then systems engineering is Roger Young and Namshla Mabombo from Sorel. Namshla is also serving as part of the control software team. Well, let me just remind you about the science case. And that is that with large surveys like LSST and then future SKA coming online, we expect there to be a very large a flood of new transient events, and these will require a some way of deciding what it is that's producing these transient events. So we're going to build a spectrograph whose aim is the rapid identification and possible follow-up of transient events that covers a wide wavelength range, rather larger than can be accommodated with the existing RSS. It's relatively easy to find transients, but identification is a one-by-one process and is best done spectroscopically with the widest possible wavelength range. Objects will have emission lines, absorption features that can be used to classify them, and maybe even their spectral energy distributions. Are they red? Are they blue? It will also help out in deciding what it is we're dealing with. a lot of the existing, a lot of known transients so far have shown very rapid spectral and brightness evolution. And this will require a very rapid response in order to make sure they are observed before they fade away into obscurity again. And SALT will be very good at this with its Q-scheduled approach. Just to remind you about what's going on with the what used to be called LSST is now the Rubin Observatory. It's a 10-year survey. It will cover from Chile all the sky that's visible at quite high cadence. The expected start of science operations is the beginning of 2023, but as everywhere in the world, there have been problems with COVID-19. There's also been civil unrest in Chile, so work on the project was stopped completely for quite some time. Then there is the problem of SpaceX and its low Earth orbit satellites, which produce bright trails on images, and it looks pretty bleak. And so far, it seems very difficult, if not impossible, to schedule observations that won't be very severely affected by these things. So there's a lot of work going on at the moment to try and figure out what to do about it. So this is slowing people down a bit as well. So with all these expected delays, maybe the beginning of 2024 is a more realistic start time for operations of the Rubin Observatory. So our aim then is to get a new spectrograph on SALT in time to start at the same time as the Rubin Observatory. We have to get on sky very quickly because as you see in the accompanying diagram, the discovery rate is quite high at the beginning and falls off very rapidly for a whole different categories of likely transient events. So one has to be in at the beginning in order to maximize the benefits of actually doing transient follow-up. Last February, we had a conceptual design review during which we presented a possible design for a spectrograph. And I list here a few of the characteristics. I don't want to go into them in detail, but the wavelength coverage was going to be 360 to 900 nanometers. Well, this is impossible to cover with a single VPH grating, so we need something else, another grating, in order to do at least half of this wavelength range. And so we need a dichroic filter of some kind in order to separate out the blue side and the red side. And the cutoff was set at around 630 nanometers, unspecified otherwise. Various performance characteristics. We're going to use an E2V 6K by 6K CCD, partly because the same kind of CCD A is in use on Sibonise already and was going to be installed as an upgrade in the existing RSS spectrograph. And we wanted full frame transfer, slot mode readouts. A measure of what we should be aiming for is in this panel here. We expected to get a signal to noise of greater than 5 for a 2x2 bin pixel for an A0 5-star with 21.4 magnitude in 1800 seconds. This is roughly comparable with what was being asked, what was asked right at the beginning for RSS. It was important to retain all existing functions of RSS if we were going to modify it in any way. And then there was to be the possibility of obtaining polarization observations with the red arm, and also of articulating it to change the wavelength coverage, as one can do with existing RSS. There was a meeting in May 2020 of the SALT STC, and after some deliberation, considering the cost and timeline implications, they decided that this was no longer a requirement. So this has now led to a simplification, the possibility of a simplification of the design. Okay, what is the system design? This is set out here in a schematic way. We have this gray box in the background, which is RSS Jule that I told you about at the beginning. That comprises a red arm, which is this top yellow box, the existing RSS, which is this box here, both of which would be fed by the collimator module, so-called. The existing RSS's light would come in, sent off to RSS via the fold mirror, and eventually out would come some data for science processing. With the dual setup, then the dichroic would be moved in instead of the fold mirror, would send the blue light to this arm. The red light would be allowed to carry on into the through the red grating and red CCD, and out would come some science data at the end. All of this was controlled by the SALT astronomer or SALT operator from a modified HMI, where it was necessary now to set up two different spectrographs at the same time in order to effect an observation. Looking in a bit more detail, looking at what the actual system would look like. Here is the telescope focal plane here. Light comes up from the bottom through the collimator triplet to a red fold mirror, through a doublet, beyond which now you have a collimated beam, which is fed through the grating into the camera, and the detector is here right at the end of the chain. Now with the addition of the red arm, we now replace the fold mirror at 45 degrees with a dichroic at 45 degrees. And its purpose is to send the blue light this way, let the red light go through a doublet, after which we now have a collimated beam presented to the red grating, to the camera, and the CCD detector. And one of the functions that I have had to serve is to decide that the dichroic would split the beam at 634 nanometers, 6340 angstroms. Well, choosing the dichroic crossover wavelength is a bit of a lottery. One has to avoid interesting features in likely transients. So we have spectra here of lots of different kinds of object. Of course, this is impossible entirely because something like a supernova 1A could be redshifted right through here. This silicon feature could go right down onto the dividing line, but that's just the luck of the draw. Then there are night skylines at the very red end, 6,300 angstroms or so. There are a couple of very strong lines, and maybe we'd like to be a bit redder than that to avoid those. And then we need arc lines in order to calibrate the wavelength scale. And we have to make sure that there are enough lines at the end of the spectrum in order to allow for a stable, high quality calibration. Then there are other slight complications that I knew nothing about dichroics before this, but I'm going to bore you with everything I've discovered. And that is that given that the dichroic's operating at 45 degrees, then polarization becomes important. And what happens if you look at the middle curve here, the green one, light that's polarized parallel to the slit. So in an unpolarized beam, expect about half the light to be, can be represented as polarized parallel to the slit and the other half at right angles to the slit. So what happens is that all the parallel to the slit light gets transmitted as we go further into the red until it's all transmitted here. It's half of the total light. So here is transmission of 0.5. After a while, the light that is polarized at right angles to the slit starts to be transmitted, and eventually all of the light is transmitted by the filter. So you've got this rather complicated region here where polarization is quite an important effect. Now, all of this is one thing. Then because we're operating in a partially collimated beam, I told you that the collimation only occurs after the dichroic. This is all smoothed out, so it looks a lot nicer and cleaner, which is this dashed line here. It's flattened a bit, but you see it takes about 100 angstroms for the filter to go from fully reflecting to fully transmitting. And this means this just has no particular implications other than this is a region that's very doubtful when it comes to trying to understand what's going on. Then there's a slightly extra complication. This is okay for the transients. So we're going to put them right on the axis, and they'll be facing the dichroic at 45 degrees. At one end of the slit, though, the angle is slightly greater. At the other end, it's slightly less. And this has a major effect on the transmission curve of the grating. If we go to one end of the grating, we move almost over 100 angstroms further to the red. If we go to the other end, 100 angstroms to the blue. This has no real implications for the transient on the axis, but there are implications to do with stray light. While this this characteristic is valiantly keeping out all of the light to the blue of this line, this one is letting through 100% of the light redwood of this line. So there are problems, but I'm sure we can get around that without trying too much. Okay, well, I'm going to hand over to Yannis now to let him explain to you in more detail what happens in the optics.
Thank you, John. Let me just share my screen here quickly. All right. So in terms of the optical design of the red arm, as John said, that starts after the dichroic. We have the red doublet, which finalizes the collimation. That's not shown in this diagram. Then once you have the collimated lights, we place the grating at the exit pupil, which then disperses that beam, and we catch that dispersed light with the camera system to image the spectrum onto the actual detector. So the grating we chose in the design is essentially a 1,200 lines per millimeter VPH grating. What's slightly different from the existing RSS is that we chose to use this grating in an asymmetric fashion. So the incidence and the diffraction angles are not the same. And so you can still get good efficiency by using it like this, by tilting the fringes of the grating with respect to the grating normal. And the reason we do that is to avoid what they call the recombination litro ghost, of the slit, which would normally form right in the center of your detector if you use the system in a symmetric at litro. So what happens there is that your spectrum can reflect back off the CCD, propagate all the way back to the grating, and by diffraction recombination gets re-imaged onto the detector as an undispersed white light image of your slit. So a ghost image of the slit right in the center of your detector, which is not what you want. So what we do is we use it off a litro, so that this ghost is actually placed outside of the detector field of view off the blue side of the system. So that's one change we made compared to Viz. The other thing, that one of the driving factors of the camera design was the fact that we had a pretty wide 22-degree dispersion angle coming from the grating. And that's due to a combination of the wide wavelength coverage we need, essentially half the optical band, as well as the high resolution we need, or higher resolution we need of 2000, and the pretty wide slit width of 1.5 arcseconds. So that means we have this 22-degree field of view that the camera needs to capture. So that was one challenge. The other was to now fit this wide spectral wavelength onto your detector real estate. We needed to demagnify the image of the slits by almost a factor of 3. So that meant a pretty fast f1.55 camera design. If you compare that with the Viz camera, which operates at f2.2 and has an acceptance angle of 16 degrees, you can see that this is a bit more challenging. But we managed to do that with a pretty straightforward, simple 5-element refractive design. We used two mild A spheres just to make sure we properly capture the dispersion angle and flatten the field at the focal plane properly. So there's 2 mild A spheres, the rest are all spherical optics. It's an all airspace design. We decided to avoid liquid coupled groups in this design. And because we are operating in the red part of the spectrum, we did not need to use any exotic glasses or crystals like calcium fluoride. These are all off-the-shelf standard and preferred glasses from Schott and O'Hara. And in fact, we have confirmed with them since CODR that we can in fact source blanks of the required sizes and these materials from them. So we have cost and lead times from the vendors on this, so which is good. So what's happened since concept review? As you heard, the decision was made to stick with a fixed grating design, and that simplifies the design a lot. It means we can move the camera closer to the grating so that the total clear aperture of the camera lenses are smaller. If it was further away, this dispersed beam would continue expanding. So basically all the lenses are slightly smaller than originally planned, which makes it easier to find blanks in the required purities and such from the vendors. The other aspect is because the camera does have some chromatic aberration, chromatic focus shift, the red light and the blue light don't quite focus at exactly the same plane. So, but if you have a fixed setup like this, you can compensate for that by just slightly tilting the detector. So that simplifies the design a lot by not trying to achromatize the entire camera assembly. That would have needed more elements and possibly some crystal elements as well. So by making that decision, we can simplify the camera design quite a bit. So how does this now actually? How do we expect this to perform? So in terms of image quality, if you look on the right here, I have some simulated images of a filled slit and a through slit image of a spectral of a stellar object. And if you look at the profile of these in the spectral direction, you can see the filled slit one there, and then the actual through slit one in green. So if you take the full width half max of the filled slit profile, you can we expect the resolution in these bottom plots over here, where the resolution is between 1600 and 2500, and a mid-band resolution of about 2100, which meets the specification. You can, of course, get a fair bit higher resolution across the band if you use the through slit stellar profile, but that does increase the crosstalk between spectral elements a fair amount, because we get some of these wings protruding into the next spectral element more. So, but if you look at the difference between the on-axis and the off-axis performance along the slit in the spatial direction, they're very similar, which means the camera system is doing a good job of keeping the image quality tight right across the field of view. And even across the spectral band, the crosstalk stays fairly flat, 3% crosstalk here, although it does go a bit higher on the very blue end, where it's the most difficult to compensate for, but still doing still well within the specification of image quality. What does this look through in terms of throughput? Well, throughput is, of course, one of the main goals of the instrument. So if we look here on the right-hand side, we have a number of simulated plots for what we expect on the red arm. On the left, we have actual measured performance of the RSS Viz when configured as the blue arm. So at the top, we have all the camera optics. The expected throughput there is in the order of 90%, which compares well to the blue camera. Just below that, if we add the rest of the red arm, so the dichroic and the red doublet, the red fold, we drop to about 80% throughput. And if we now add the grating efficiency as well as the quantum efficiency of the detector, we get down to this green curve here, which still easily meets the specification that John mentioned earlier. And then the end-to-end throughput for the whole instrument, so from the slit to the detector, including slit losses and detector quantum efficiency, we get this gray graph over here, which peaks at about 44% throughput, and it compares well with what we're currently getting on the blue arm RSS Viz. So I think we're doing fairly well on the design side. What does this mean for on sky? So here we have on the left an A0 5-star, magnitude 21.4. And if you look at the photon flux, the photons per second per angstrom here, it peaks at about one photon per second per angstrom and drops down from there. If you compare that to the sky background, the continuum here is at about 5 times higher, 5 photons per second. And then also you have these bright skylines, redwards of about 7,000 angstroms, getting more and more prevalent. And this is one of the reasons why we needed a higher resolution on the red arm to try and isolate as much of the lines as we can. So what does this mean for us at the detector? So in a 30-minute exposure, 2x2 binning, this is the electrons per bin pixels that we expect. And converting that to signal to noise, in the middle here, that's about 6 to the specification. We try to reach about 5. So we're doing well in the central band here. Actually, the monotonically sort of decreasing photon flux of the star is bumped up again here in the middle here by the red arm. So we actually improving on the normal sort of slope here. So we're doing pretty well there. At the very red end, it does start to drop down a bit. That's mostly due to the quantum efficiency dropping down on the detector, which we can't really do much about. Of course, this is 2x2 binning. You can easily expect to do 4x2 binning more in the spatial direction if you want to improve the signal to noise even more. So I think we're doing pretty well in terms of our original goals. With that, I'm finished on the optical side. I will hand over to Ocker to talk more about the system design.
This is always going to pick the right screen to share. I hope this is the right one. So how does all of this look when we put it on the existing instrument? And shown here is the layout of the instrument as we currently see it. Light comes in from the bottom, and this is kind of a top view. And I'll just list the components that's of interest to this project really. The first thing that we hit is the dichroic fold assembly. This is a mechanism that holds a fold mirror and the dichroic and slides in and out. Pneumatically driven mechanism. And next, we'll see the red doublet before the light gets folded by the red fold into the grating, to the triplet, the focusing lens, shutter over here before it finally hits the detector. Also shown in this picture is the IDSAC. That's the detector controller that is produced by Yuka. And you'll see several of them over here. Catherine will talk a little bit more about it. And then we've got a single enclosure here for all the electronics, detector electronics of both the red side and the new visible detector upgrade. We also shown in this picture is a space allocation for the Echelon controller assembly. That's an upgrade happening in a different project, but it does impact a bit on our space allocation. And I think the only thing I haven't shown you is the frame. Sorry. Just a little bit more detail of how we mount the camera and Dichroic to the existing RSS frame. You'll see here there's a couple of main components. The yellow frame you can see, which holds basically the doublet, the fold, and the camera grating. And then just below it, you'll see a maroon frame holding the Dichroic fold assembly. You know, it also provides support for the visible doublet. That whole system is supported in the center with, you see here, there's a central support, which all of these bolt to existing interfaces on the RSS frame. So in terms of at least mounting the instrument, it's quite easy to do. Currently, the concept is for these frames to be made out of Invar. We have some leftover stock from when they actually built this original RSS Vis frame, and we're going to try and reuse those components. The picture shown here is still a work in process, so there's a lot of details that still need to be added. There's also some structural elements that are not shown here. For instance, the support of the optics is not developed fully, and that's what we'll tackle next. Next up, I think Catherine will speak a little bit more about the detector systems.
Thanks, Orchid. Same story. Let me see that I can share the correct screen. Right, morning everyone. So from a detector point of view, SAO instrumentation is developing the detectors for both the red and the Viz systems that we've spoken about this morning. So even though this is a MaxE project update, there are aspects of the detector that I'll touch on that concern both projects. So just, you know, sort of at CODR, what we knew is we would use these Teledyne 6K by 6K detectors. So I'm going to do a complete cop-out here and say we have issued the purchase order for those. We managed to do that last month. And for the details on all the ways, like the decisions that we made and the choices we were faced with in that selection, I'm going to direct you to last month's newsletter. For the guys not in SAO, I'm sure you can get hold of me or Routurd and we can send you a link. But just a recap on what that looks like. So it is a monolithic 6K by 6K chip. We contrast this with the current Viz setup, which is 3 chips that are mosaic together. The new chip has the same sort of operational waveband that we're interested in. We are taking a little bit of a hit in Viz on the QE on the blue end. Those 3 chips that we have currently, you have the freedom to take the one that has the best performing blue QE and stick that on the blue end of the detector, whereas now with a monolithic chip, we can't do that. So we are taking a little bit of a hit there. The broadband coverage of this is sort of quite excellent in general. To try and mitigate, Teledyne have offered us a coating that they haven't put on this large format chip previously, but they'll do that for our chips, and we should get a slightly better blue performance than the standard coatings. Some technology on fringe suppression and deep depletion. There's a nice comparison shot in the newsletter, but that fringe suppression result is looking quite excellent. Cosmetic specification, we went with the best one possible. I'll chat on what cosmetic defects look like on the next slide. And then there was just a choice of two geometry packages, and we thought about it a bit, and in the end decided to go with the one that we had the most experience with already. So with this chip, we're using as Orchid mentioned, we're using the controller developed by IUCA, the IDSAC, IUCA Salt's Indian partners. And this architecture duo, the 6K by 6K chip with the IDSAC is being used in Sibonise currently, which is an instrument that we put on our Lesedi telescope earlier this year. A lot of the effort this year has gone into just sort of reliably understanding the communication required, to the IDSAC from the IDSAC, optimizing various parameters. And here's just a snapshot of the GUI that was developed for the Sibonise installation. So look at those pictures. You have the Sombrero Galaxy on the left that was taken with the chip that's installed currently. On the right, you've got M83, and Villiers superimposed the circle is representative of the size of the moon in that field. So focusing on M83 in the middle image now, just a couple of features to point out. You'll see these white lines, these vertical white lines. Those are column defects. This is an electrical sample that's currently installed. So it's not the final science chip that will be in Sibonise, which is of a much higher cosmetic quality, which places a cap on the types of defects that are present on the chip. So an electrical quality makes no promises about actually being able to get an image out. It just promises to be to give a correct electrical load at the controller. So we're quite lucky that this one does produce images. There is a there's a horizontal line, a sort of color mismatch that you can see across the image. There is a vertical one as well, but it's tougher to see in this image. The CCD has a 4 amp readout, and we'll see the controller can read in the 4 amp readout. There is some sort of relative gain differences between the 4 amps, and a lot of the effort currently is figuring out, well, what are our options? There are various amp readout configurations that the controller could possibly do, and so our team is in communication with IUCA to figure out the best, sort of optimization methods there. What else we did since CODR? We said we'd build a test cryostat, so we did. The test cryostat allows us to test a whole bunch of things before, we have an actual cryostat ready. IDSAC functions, temperature control loops for keeping the CCD at a constant temperature. We're developing custom PCBs for the connectors through the walls, so this will allow us to do that. Initially, liquid nitrogen cooled, but it does have the capability to stick on a cryotiger as well. Just also a snapshot of the work in progress on the actual science cryostat layout. So the goal here is for the red cryostat and the vis cryostat to make them as far as possible clones of one another. And just pointing out this maroon plate that you can see, this is essentially the interface plate that will hold that final lens, that field flattener that Johannes was talking about, and be the interface with the rest of the camera barrel. So the idea is that everything behind that is as far as possible identical between the two cryostats. And that gives you the possibility, if one goes down, to unbolt the other one, if needs be, and stick it on with minimal downtime. Also, standardizing on components is fairly important. So things that Salt has inventory of, has experience with. Just pointing out some of these components. The big round thing is the cooler. Gives us a 165 Kelvin or so temperature for the CCD. We've got a vacuum valve. We've got the standard sort of ion pump that we use at the bottom here to maintain vacuum. The connectors look like they're floating in sort of midair. Those are, after a fair few rounds of conversation, fairly particularly placed for, sort of maximum functionality. We just sort of have to work an enclosure in amongst all these components. Hiding behind all of this is the actual CCD, which I will show you here in this view is a bit better. So that's the front of that assembly is, it's the silicon face of the CCD that's open to the rest of the optical path. The blue thing is a frame transfer mask. Neither detector, neither system will use the full spatial range of the CCDs. So we're able to put a frame transfer mask. It also acts as a bit of a heat shield, which is nice. The back of it, the chip comes with these 3 studs. So we use that to mount onto a carrier frame, bolted to the rest of the housing, and all the orange bits inside there have to do with controlling the temperature. We provide a really cold surface, but then we also have some heaters to modulate the temperature so that it keeps really stable. And then this is the last one. Orchid spoke a bit about the layout of the instruments, and this is quite an exercise. So we've managed to, Tabua did a lot of sort of figuring of what the various components were needed for the the two systems, it's not just a detector and a controller. There are a whole bunch of other things. There are ion pump controllers, power supplies, PLCs, all sorts of telemetry equipment, and that has to go somewhere, and it can't go sort of, right near the cryostat. So what he's been able to do using these sort of 19-inch sub-rack configurations is stick the electronics for both in the footprint currently enclosed by the SDSU controller that's on RSS at the moment. So that is the box that has the current detector electronics. And we're able to, with there's still a whole detailed design exercise, but we're able to replace that with the electronics for both systems, which is quite exciting because finding space for a second system was going to be really difficult. And it also helps with our sort of mass being able to use one enclosure. Something that's a bit more difficult is, I need to make the point that things are spatially, in this enclosure, things are spatially in the same place, but they're functionally separate. So we're not combining functions into one piece of equipment. There are still two separate ion pump controllers, two separate power supplies for things. So we don't take out one instrument both instruments with a single point of failure. There are purple boxes everywhere. If you look on the Viz side, there's one here, there's one in front, there's one hiding behind here. On the red side, you've got one either side and one up there. And that kind of reflects the current effort and state of thinking in trying to find a place for the detector controllers. So we have a 300 millimeter cable limitation between the detector and its controller, unless we want to introduce sort of active components and extra heat load, which we don't really. Current efforts to try and find a sensible place for it, and we'll knock out sort of some of these options as they prove to be unfeasible, and hopefully get left with at least one option per detector. I think that's the summary of the detector side. Routurd got the last slide just on project and schedule, so I'll hand over to him.
Hey, thanks, Captain, and hi, everyone. So I'll end off with the latest on the project schedule. So this slide gives an overview of the various phases and the major milestones in the MaxE project. It starts from the project moving through the concept design and the preliminary design up to commissioning. The red shaded line at the bottom indicates the RSS Jule's so-called window of relevance, which is driven by the LSST commissioning timeline, as John Menzies mentioned earlier. And this is the target of when we want to have MaxE available or RSS Jule available. The next major milestone for MaxE is the preliminary design review towards the end of 2021. So that's in the red box above. We have made a decision to procure the optics after the PDR to reduce risk. The optics design is relatively mature and has been for some time. But since this is an upgrade to an existing instrument with space and weight constraints, we need to get the opto-mechanics and the overall mechanical design at a sufficient level of maturity. And this gives us an extended preliminary design phase. There's also activities we're doing to get the exact build of the current RSS, the dimensions up to millimeter level. So that's all part of trying to get the design matured. Note that there are quite a few upgrade projects happening on RSS Viz during the same period. There's the doublet repair, there's the triplet upgrade, there's a 700 rating upgrade, there's long slits, and also the Viz detector upgrade that Catherine spoke about earlier. These are the so-called Big Five projects, and it's under the overall coordination of Lisa Krause, Lee Townsend, and Keith Brown. These projects are being installed ahead of MaxE or ahead of RSS Jule. So there may still be changes to the MaxE schedule to accommodate these Big Five projects, and this is currently being figured out. So that's all from my side on project schedule. I'll hand over to John again to take us through the questioning session.
Yeah, it's a great teamwork, and thank you all for the wonderful presentations. Yes, we can move on to questions now.
It seems like a perfect exposition on the part of the team, and everybody's happy.
I think I've got a question.
Yes, yes, Vanessa.
Yeah, it's Vanessa here. Thanks, John, and thanks for the team. That looks very exciting. I think I just missed a couple of things. So for me, the new part was, so as part of the MaxE project, it's also including the upgrade to the blue arm on RSS. Is that right?
Maybe I can take that one. So it's not that the projects themselves are the same. That, you know, they, from a detector point of view, because the physical systems are, you know, as identical as possible within that development team, you know, we're looking at them as one. But it's not to say that the Viz upgrade is part of the MaxE project. It's just from a detector point of view, there's a lot of shared effort at this point.
Okay, cool. That sounds sensible. And then one other question, which I'm sure you must have showed in the slide and I missed, that what is the pixel size in arc seconds?
Maybe I can take that. So what I can tell you, I don't have that off by heart, but what I can tell you is that the plate scale on RSS is 118 micron, micron per arc second, and on the red arm it'll be 78.
Okay.
So, and you have 15 micron pixels, so you can work from there.
I should do that.
Yeah, I think it's
So actually it's
0.125, something like that.
Yeah, it's 7.8 pixels per resolution element on the red side. That's for 1.5 arc seconds. It's 7.8 pixels.
Okay, cool. Thank you.
Any other questions?
Hi, it's Steve here. Can I ask a question about the schedule, please?
Yes, Chief.
So on the schedule, can I ask, is the schedule deliberately fitted in to meet the date of the LSST 2024, or is it just, you know, is that the time frame that you think you can get the instrument built in?
It's a latter. So we had to think about when the instrument will still be relevant, because there's no point having it there and then we miss the main science purpose of the instrument.
So I guess my follow-up question then is, can it be done in a quicker time?
Can it be done in a quicker time? No, I don't think so. Unless we have more people on the project or something like that. Because we're a bit light on opto-mechanical resources because of these big 5 projects that are prioritized. And that's actually determining the PDR schedule, the opto-mechanical resources.
Okay, thanks.
Routurd, can I ask a follow-up to what Steve just mentioned? Having pointed out that it is the science which is driving that end date, which really, ideally, we'd like to have even sooner. Do you have the resources to actually meet that and complete the big 5 in parallel as well? So in other words, where are the crunch points here? Where are the really key resource issues to help you meet this schedule?
So as I said, the opto-mechanics is the real schedule driver at this stage, because you made this decision to procure the optics after the PDR. And at the moment, this reprioritization effort of having the big 5 installed ahead, that is still being figured out. That's going to have an impact, most likely, on our PDR schedule. So I'm working with Lisa and Lee and Keith to exactly find out how much of Janus and Orchid and Milani and so on is going to be needed and when. So yeah, we need a bit of more time to figure that out. But the PDR is a real important milestone because it kicks off the optics procurement, which has a lead time of about 12 to 16 months.
Indeed. So if you're going to need additional resources to meet that, you need to identify that as soon as possible.
Yes, yes.
Okay, thank you.
Okay. Any other questions?
I have a quick question.
Yeah.
Why does the dichroic have to be mechanized? Can that not be a fixed unit?
I can quickly take that, Heinik. So yeah, the main reason there is that we need to retain all the current RSS viz, performance and capability. So the current red side that dealt with RS viz for say spectral polarimetry and Fabry-Perot, all those things still need to be able to happen. So we need both a single beam, current RSS, as well as a dual beam, which is spectroscopy only.
Okay, so when the dichroic is moved out, there's still a fold mirror in there.
There's still a fold, yeah. So you switch out either the fold or the dichroic. So yeah, so in the fold mode, you have the full current RSS single beam capability available.
And this is articulated with that set of 6 gratings you can use, so you can cover a much higher resolution in the red than we can with the red arm.
Okay.
Can I ask another question about the throughput? You showed some throughput plots, but unless I missed it, I mean, the visible arm of RSS can already do the red, right? So do you have a comparative plot of the known throughput of RSS in the red compared to the expected throughput of the red arm?
So not.
I haven't. I could do that, Steve. I haven't actually done it. It's been a bit difficult.
I mean, I'm in my simple mind, I'm just thinking, the one reason why we're building the red arm, I mean, it's a bit pointless to build the red arm unless the red arm has a better throughput than the red throughput of the current visible arm, right?
I think
what I'm thinking is there such a comparative plot that shows how much better the red arm will be?
So Steve, just to jump in there quickly, first of all, I don't have one available at the moment, and that can certainly be done. The main aim, though, is to get the simultaneous wavelength coverage of double the current coverage that you can with viz. So that's one of the big drivers for adding the second channel, because you want the simultaneous wide wavelength coverage. Otherwise, yes, you're right. I mean, you can use the current red system. Although, yeah, I'll have to look at those plots. I know that the current 900 rating does fall off quite a bit in the red as well. The wavelength coverage simultaneously.
There is also the resolution increase in the red to give you a bit more room, elbow room in amongst the night skylines.
Right.
Yes, which you can't get with a 900 rating.
Very good, thanks.
Cool.
Can I ask another question? Really, this is for Orchid. For Janus, because I thought your I was impressed with your optical design, the level of detail, and Ockert's structure to hold it. What is holding you back from bringing the PDR earlier? Are there really? I didn't detect any of you talking about major problems, and just realized the PDR on Routurd's schedule is a year away. What is? Is there anything that is really stopping you doing it a bit faster than that?
I think Ockert can best take this, but otherwise there's still a lot of iteration with vendors just to ensure that what we're asking for can be made within tolerances and all that. But that's the kind of the normal iteration you would go through during procurement. That might influence the final design a bit, which takes a bit of time. But I think Ockert can comment mostly on the optomechanical design effort that's still required, which will also feed back into the optical design eventually.
Yeah. So I think a lot of the work that still needs to be done is the simulation of the structure, to look at the flexure specification. There's quite a tight spec on flexure for the system. So flowing down those tolerances to the design, making sure that we can actually meet the specification. That'll take some time. There's the detail. So there's a lot of the iterative work that needs to be done that's kind of difficult to plan ahead for. So we took our big step at how long this will take and to get to a reasonably mature design to support all the optics.
And there's also the aspect of really understanding in detail the current RSS collimator performance and design to make sure we match up our red arm to what is existing on the instrument. So as part of the doublet, the new VIS doublet installation, for instance, we would like to do more metrology and measurements and optical testing on the existing RSS collimator, possibly making some small adjustments to optimize that collimator performance, and then make sure we match our optical design to that before we approach manufacturing.
No, I understand that. Yeah, but it just seemed to me that the red arm with a fixed grating, and you said you'd gotten the lenses smaller. It seemed that ought to be easier to meet the same specifications that you're already achieving on the visual arm. Or am I missing something?
Well, I think the trickier bit there is because we have we need the higher resolution in the red. So we have, as I said, the higher dispersion angle. So it's a wide angle camera, which is more sensitive. You need some A spheres on it. So that would complicate manufacturing a bit. So it's a bit more tricky. So you need to be careful in specifying that correctly and the testing method for that as well. And then just, yeah, as I said, just making sure the as-built RSS is understood really, really well. So you can actually make sure the rest of the optical design is optimized for that correctly. That's an important first step that we need to get out of the way, which will take a bit of physical testing and time as well.
Okay, thank you.
Any other questions? Okay, if no more questions, it's almost time, and I think we can wind up. Let's thank all the speakers again. It was a wonderful talk and presentation from everyone, and nice questions. See you all again. Thank you.
Thanks everyone for joining.
Yes.
Thanks, Jessica.
Thanks very much. Ciao.